So now let's talk about general 3D stress. The reality of stress is that it's in 3 dimensions. Just like the world has X, Y, and Z in space, so too does the stress that's transmitted through a body. Now, often in the general case of stress, we'll define it in terms of X, Y, and Z. We'll have our normal stresses, sigma X, sigma y, and sigma z, which are the stresses on the surfaces of a body. But then also we'll have our shear stresses, such as tau xy, tau xz, and tau yz, which represent the shear stresses across the surfaces. Now, this general state of stress, there are 6 terms, but we also could take that general state of stress and find an orientation to section that 3D stress element and find an orientation where the normal stresses are maximized, meaning we find the principal stresses. We also could find another orientation where the shear stresses are maximized. We call those the extreme valued shear stresses, where the overall maximum is going to be tau 13, which is the overall max. Now, how do we deal with this case where we have 3 principal stresses or we have 3 extreme valued shear stresses? Well, Moore's circle in 3 dimensions is plotted as follows. We still have the x-axis as normal stress, and we have the y-axis as our shear stress. But instead of just drawing one circle that represents one plane between x and y, instead we're going to draw 3 circles that represent the planes between x and y and z, and z and x. So we'll have 3 sets of Moore's circles to give us that 3-dimensional state. Now, in these 3 sets, there's a couple of key points that we need to find. Of course, on our x-axis, which is normal stress, we will find our principal stresses, the largest principal stresses possible. For the largest value, sigma 1, second largest, sigma 2, and then the smallest is sigma 3. And then in terms of the radius of our 3 circles, the radius of our circles are the extreme valued shear stresses that sit between sigma 1 and 2, and that sit between sigma 2 and 3, and that sit between sigma 1 and sigma 3, with the overall maximum extreme value shear stress being the largest circle that we see. Now, in our previous examples, or in the previous video, we only had 2D stress, and we had a whole bunch of equations, stress transformation equations, that helped us find those principal values. But for a 3D problem, we have a different set of equations to find those principal stresses. Finding the principal stresses, those 3 values, is a root finding exercise where we have a polynomial of stress, sigma 3 minus identity 1 times sigma squared plus identity 2 times sigma minus identity 3 equal to 0, where our goal is to solve this polynomial for the value of sigma. Inside this polynomial are 3 identities: identity 1, identity 2, and identity 3. And these identities are calculations from our basic stress tensor, where, say, for example, identity 1 is just our normal stresses added together. Identity 2 is multiplications of our normal stresses with subtractions of some of the shear stresses in our stress element. And then identity 3 is a bit more complicated. All 3 normal stresses multiplied by each other, plus 2 times all of the shear stresses multiplied, minus normal and shear stresses in a certain configuration. But if we are given our stress element, if we know our normal stresses and shear stresses, we can calculate these identities, and then we're left with this polynomial that we need to solve, and we can just throw that in our calculator. Throw it in a a TI, 86 calculator and solve for those solve for those stresses. What's important to note, however, is the order of the stresses. The largest principal stress is sigma 1. The second largest is sigma 2. And the smallest is sigma 3. So we sort them by their magnitude. Our extreme value shear stresses are easy to find. If we have our principal stresses, then tau 1, 2, where tau 1, 2 is sigma 1 minus sigma 2 divided by 2. Tau 2, 3 is sigma 2 minus sigma 3 divided by 2. And tau 1, 3, which is our maximum, is sigma 1 minus sigma 3 divided by 2. So in essence, we're taking the diameter of each of those Mohr circles and dividing the diameter by 2. That's all we're doing here. Now, another important point for our 3D Mohr circle is where our average normal stress exists. It is the center point for our biggest diameter circle. And that average normal stress is going to be sigma 1 plus sigma 3 divided by 2. It's where our absolute maximum shear stress exists. So with this basic knowledge, we're able to find the principal stresses for a 3D problem, as well as the extreme value shear stresses for a 3D problem. These stresses, the principal stresses and the shear stresses, can often tell us the directions where failure will occur in materials that are brittle and materials that are ductile. But let's wait. We'll find out more of that in a couple of lectures.